Okay, in chapter 4, we're really gonna lay the foundation for a lot of what's to come throughout the rest of the course. We're gonna start talking about Newton's laws of motion. So we're gonna get away from uh, the kinematics of motion, just the description of motion itself, and we're gonna start getting into the reasons why things move or the dynamics of motion. But first, we need Newton's laws before we can start talking about. So things we're going to cover in this chapter are understanding what a force is, either as a single force or multiple components of a single force or multiple forces, and then the sum of these to find a net force. Newton's first law, Newton's second law. We're going to also talk about the difference between mass and weight. Talk about Newton's third law. We're going to cover a very important method for analyzing physics problems, and that's called a free body diagram. So we'll go over how to set that up, and that's crucial to being able to solve many problems that come up in the later chapters. In chapter 5, we'll cover specifically applying Newton's laws and free body diagrams. So 4 and 5 kind of go together. Coverage for this chapter is just 4.1 through 4.6. So like I just said, in chapters 2 and 3, we focused on just the description of motion, which we call kinematics, and now we need to get into the dynamics of motion, which is why things move. So in order for something to move, it must be caused. The motion must be caused. And so what causes that motion? Hopefully you say that a force would have to cause this motion. So either we need a pushing or a pulling, something to cause it. So what a force is that it gives us a quantitative description. It gives us a numerical description of how two objects interact, the interaction between two objects or an object and its environment. We have different sorts of forces. You can have a push or a pull, would be a contact force, in which you have a contact, a force F here, being the contact is the push, and then we have a force F here, and the contact is a pull, and it's the contact is through the string, right? We also have some forces that can act over a distance, right? Gravity acts over some distance. It is not a contact force, but it's still a force nonetheless, because it'll cause something to move down. If I drop something, it will cause motion downwards, right? But it's the earth pointed down, but the earth isn't actually touching this ball here, right? So it's acting over some distance there. So we have you can have contact forces, you can have forces acting over some distance, and other sorts of forces we'll get into later. Does the direction of force matter? Does it matter? I mean, this is F right here going to the right, and this is F right here going to the right. Is that the same thing as F going down? No, definitely not. The direction that force is applied definitely matters. Force is a vector quantity. It has both a magnitude as well as a direction. So direction definitely does matter. Some types of forces. We think about a couple different types of forces here. We talked about contact forces here. We talked about forces over distances we have here. So some of the types of forces we have, we can have a single force, or we can have a net force. A net force would be, if we had several forces acting, we could add up all of them and find out, it's just a vector sum, find out what the vector sum is. And that would be we can turn that into a single force. So we can take a net force, multiple forces, and treat it just like a single force. So for these, we can have a contact force, F, which we saw with the hand pushing on the block on the other screen. That's a force between two objects when they're touching. That's a contact force. We have a normal force. Normal means perpendicular. In physics, so we have a normal force is perpendicular to the surface. I have a surface that the block is sitting on right here, and then I have some normal force pushing up here, and this normal force is actually counterbalancing its weight. It weighs something, right? It has some weight, gravity's trying to pull it down. We have a normal force that keeps it from falling. So the normal force is just some force that goes outward from the perpendicular surface, right? So it's sitting on here, normal force works out like that. It's sitting on this surface and it goes outward from that surface. It keeps it from falling into the surface is what the normal force does. So it keeps it, from moving this direction. So it pushes it back like that. So that's our normal force there. We also have a frictional force. As long as there's friction present, which there pretty much always is, we will assume there, in some cases, things are frictionless just to simplify the problem for a while, but we will put in friction later on. And friction is just a force that opposes motion. Like if you were to try to slide something across a table, eventually it would come to a stop, and that's because there's a frictional force. If our block is moving over this direction, the frictional force would act the direction opposite motion, and it'll cause it to slow down. Anytime you slide something across a table, it ultimately comes to a stop. That's because of the frictional force. And the frictional force is actually tied to the normal force. Kind of makes sense. If I have a really heavy object, it actually increases the frictional force. If I have something just gliding across the top, barely touching it, maybe like a hockey puck or an air hockey puck, they have hardly any normal force, so they actually have less of a frictional force. But we'll get into more of that later. But so we have a frictional force is another type of force here. Tension. We talked about a hand pulling on a string on the previous slide here. I said it was like contact force, but really what I meant is that when the string touches the block, that was the contact force. Contact forces, things have to be in contact. But when we talk about a tension force, the hand is applying some tension to the string, which is applying some force to the rope. So the string works as a tension force. So tension is always things like ropes or cables or chains or something like that, and it's always a pulling force. I can't have a tension force. If my hand were to push here, this string would collapse, right? And I couldn't actually apply any force here. So tension is always a pulling force. So tension is a pulling force exerted by some rope or cord or chain or something. And we have weight. Weight is also known as the gravitational attraction force. So we have some weight of something. It pulls it down. It's mass times gravity is the weight. And that acts over some distance, right? Like we were talking about in the previous slide. So we have contact forces, we have normal forces, we have frictional forces, we have tension, and we have weight. The main forces we're going to talk about in this chapter. We will add a couple more forces later on, but these are the ones that are going to get us started off. Okay, so I talked about a net force a couple slides ago. I said that we could break a force into its components, and we can add them all up, and we can put them back together to get one vector or one force, right? That's what we call our net force. So we'll call this the resultant of forces. We have two or more forces acting on the same point at the same time. It's the exact same as if a single force acts on the object equal to the vector sum. So let's say I had some force here, force y, force in the x direction. I can find out, using what we learned back in chapter 1 in basic trig, we can find our magnitude and we can find the angle theta at which it acts, and we can find the resultant f if I had two forces. This is actually shown a little bit better here, maybe fy, fx. I can add these together, I'll get f, right? F acting as some angle. Very similar is how we broke apart the x and y components of velocity and acceleration in the previous chapter. We're just doing this again with forces, so a whole lot of components. Similarly, if I were just given one force, if I can take two forces in different directions, add them together to get one force, I should also be able to sort of decompose this one force into two different forces in the x and y directions. If I had a third direction, I could also decompose it into a z component as well, x, y, and z. But we won't get into that in this course, so we'll just break it into two directions, the y direction, and the x direction. So if I were given some force here, some angle theta, I would have the x component of the force would be F cosine theta, Fx is F cosine theta, and the y component, Fy, would be equal to F sine theta. This theta here. The net force is, net is you add up everything and you take something out. It's your like if you were getting a paycheck, your net pay is your gross pay minus whatever you have to pay in taxes, etc. Right? So same thing with forces. It's what we start out with, and then we kind of add up all the different components. If I had something, have some positive here and some negative there, they would sort of wipe each other out. So I'm going to do the same thing here and get my my net force is the resultant of all the forces. So I just add up everything, and again, like we had the velocities, it was hard to just, if I had a vector off like this and off like this and off like this, it would be hard to just add those vectors straight up. So what we do instead is we break them all into their components. So first thing that you have to do is do a little bit of basic trig, break everything into its components, then we'll add everything up and then put it back together to get one resultant. So we call this the superposition principle. So my resultant is the sum of all, this is a Greek sigma, it means sum, so it means add up everything. So the resultant is equal to the sum of all the forces, which is equal to force 1 plus force 2 plus yada yada yada, all the way up to, if we have 500 forces, we add up all 500 of them. But like I was saying a second ago, it's not necessarily very easy just to add the forces, the vectors, so it's much easier to algebraically add the components. So we'll say, well, the resultant in the x direction must be the summation of all the forces in the x direction. So we can say this is force 1x plus force 2x plus yada 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 all the way up to force 500x. Same thing with the y components. The resultant in the y direction would be summation of forces in the y direction, which is all these up to however many forces we have. And then once I have the resultant in the x and y, we use the same stuff we used in previous chapters to get the magnitude and the angle theta. We don't necessarily always have to have our x and y. We don't necessarily have to have y always be vertical and x always be horizontal. Sometimes it's going to be much more convenient to talk about our x's and our y's, or our y here and our x here, in terms of the perpendicular component and the parallel component. This is, if you remember back, we defined the normal force to be perpendicular to the surface it's sitting on, right? So the y component is the normal direction, right? Perpendicular. And then friction always opposes motion. Friction is always parallel. So this would be the direction in which I have my my frictional force here, would be along the parallel component. And remember, there was a relationship between the normal force as well and the frictional force. So being able to break something into its components, the normal and essentially frictional or parallel components, then it'll make problem solving a lot easier. So we're going to need to learn how to break components into their parallel and perpendicular, or break forces into their parallel and perpendicular components, instead of just always saying, y component is vertical and x component is horizontal. It'll make life a lot easier, and we'll get into kind of how to do this here in a second. But and again, this force here, we can, if we know this angle right here, we can very easily break this into an x component and a y component, right, as illustrated here. Remember, I said this already, but I want to emphasize it. Friction always opposes motion. If this is moving up here, then friction has to be working that direction. If this were sliding down the ramp, then friction would be working up the ramp. So friction always opposes motion. Which direction is the normal force? I think I already gave that to you guys, but the normal force is acting along the y direction, right? That's why we broke it into this perpendicular component, because that is normal force. Which direction is the frictional force? is if we, let's say he's pulling this up, if he's pulling it up the slide, then frictional force is moving. I'm sorry, if he's pulling this up the ramp, then the frictional force is acting down the ramp. Okay, before we get into using the components of forces extensively, let's first look at Newton's law. So Newton's first law says that anything in motion will remain in that motion until a force acts upon it. So think about before we look at all these pictures over here, let's think about what would happen to a puck that's sitting on a table that we don't touch, and it's sitting on a flat table, so the effects of gravity aren't accelerating it at all. What would happen to that puck if we don't touch it at all? Obviously it's not going to move, right? So Newton's first law kind of holds there. We didn't touch it, we didn't apply a force, and so it didn't move. It stayed exactly in the motion it was in, sitting there with zero acceleration and zero velocity until we touch it. And then if we push on it, so if we look at A here, and we look at, so what happens if we push it along a rough surface, like we're doing here, then we push it with some little force and it moves some short distance there, and it slows down, right? If we were to push it along an icy surface, so we have less friction, the smoother the surface, the less the friction, and we'll get into kind of coefficients of friction a little bit later in chapter 5, then it's going to, so what we have, if we push it along an icy surface with less friction, this is in B, so we push it here in B along an icy surface, then it's going to move further, right? This is because we have a smoother surface, so we have less frictional force acting against it. The reason it slowed down so quickly here is because we had a frictional force acting against the motion, and so it opposed the motion and it slowed down, came to a stop. All right. I also, when we push it here, there's less friction, so there's less of a force acting on it, so it goes further. And Newton's first law holds true there as well, because it'll move in a straight line unless it's acted on some other force. That force is friction here, but we have less of a force, so it moves further. If we push it along a bed of air, then so there's even less friction, then it's going to move even further, right? This is something that we would know from just everyday observations, right? So if I reduce the friction even more, then I reduce the force even more, and it'll slide even further, because it only stops if we if there's another force acting on it to change the velocity, to accelerate it. So Newton's first law just says that any object will stay in the motion that it's in unless it's acted upon by another force. Then a puck would have stayed, if we didn't touch it, then it would stay sitting still. If we push on it, then if there was no friction, it would slide forever, right? But since there is a large frictional force here, it comes to a stop abruptly. If I reduce the friction, it moves further, but still comes to a stop. And if I reduce it even less, then it comes to then it goes even further, right? It comes to a stop much, much later. So that's Newton's first law. What Newton's first law says is that every object continues either at rest or in a constant motion in a straight line. Very important that you say in a straight line, unless it's forced to change by that state. Change that state by forces acting on it. So the question I asked a second ago about what happens to a puck sitting on a table if you don't touch it may seem very trivial, but that is Newton's first law. If I don't touch it, it doesn't move. There is no force to make it move, so it doesn't move. So it continues exactly in the motion it was in until it's forced to do something. So it doesn't move until I touch it, until I push on it to move, right? The other three cases, A, B, and C, if I push on it on a rough surface, I push a little bit, but then there's a frictional force which actually slows it down. As I reduce that frictional force in B and C, then there's less force acting on it when it is moving in a straight line, and it moves further. It takes longer to slow it down, but nonetheless, it does stop eventually. So how the velocity changes is directly related to how much force is given to it, right? The harder I push, the farther it goes, the faster it goes, right? The faster it goes, which relates to the farther it goes. We know that from chapter 2. So how do we know how much the object moves when we apply a force? We know that it's direct, but we don't know exactly how much. If we were to push on a piece of paper with the same exact force that we were to push on a boulder, then which one is going to move more? Obviously, the paper is going to move much further than the boulder, right? So started thinking, all right, well, I could push with the same force on different size objects, and the smaller one is going to move much further. It's not really, size isn't as big of a deal as it is the fact that the paper weighs less, or more accurately, it has much less mass. So we have to consider an object's resistance to change, is what we call it. The mass is sort of the object's resistance to change, or more accurately, inertia. By definition, inertia is the tendency of an object to remain at rest, like the puck, to remain at rest until we push on it, or continue moving in a straight line once it's in motion. So it's how much the object wants to keep doing what it was doing, right? And we've quantified this to be the object's mass. So we say more massive object has more inertia. It takes more force to start it moving, or more force to stop it moving. You have a baseball coming at you that you can stop pretty easily. You have a train coming at you that you cannot stop very easily, right? They might both have the same speed, but you need to apply much more force to the train to stop it than you would the baseball, because it's much larger and has much more mass. It has much more inertia. So we have this relationship that the force is related to the inertia, or the mass, as we'll call it from now. Okay, very much related to Newton's first law is Newton's second law, that says the acceleration of a particle is directly proportional to the force acting on it, which we said previously, right? The acceleration is directly proportional to the force acting on it. The units of force are defined as newtons. They are newtons after Sir Isaac Newton, and they're defined as the amount of force that accelerates a mass of exactly 1 kilogram at a rate of 1 meter per second squared. So why does it matter if it's 1 kilogram? Just like we said on the previous slide, because we need different forces for different masses, right? It's inertia. It matters if it's 1 kilogram because of inertia. And we said that force is a change in motion, right? So acceleration is a change in velocity, which changes your motion, right? So we define 1 Newton of force as the amount of force that accelerates exactly 1 kilogram of mass at a rate of 1 meter per second squared. So let's run through a couple little quick examples of this. How many newtons would it take to accelerate 5 kilograms at a rate of 1 meter per second squared? Well, 5 kilograms at 1 meter per second squared. Now I know that 1 newton is 1 kilogram at 5 meters per second squared, and since I have 5 kilograms, but the rate is 1 meter per second squared, then it's simply 5 newtons. How many newtons would it take to accelerate 1 kilogram at 5 meters per second squared? Well, the 1 kilogram is the same as we have on our definition of a standard newton, but now we're accelerating it as 5 times as fast. So again, we have 5 newtons. How many newtons would it take to accelerate 5 kilograms at a rate of 5 meters per second squared? Well, if it's 1 kilogram for 1 meter per second squared is 1 newton, now I have 5 of each, and I have 5 times 5, or I have 25 newtons for 5 kilograms at 5 meters per. Um, the vector form, the equation for Newton's second law can be written as force is equal to mass times acceleration, right? We had 5 kilograms at 5 meters per second squared, so we had 25 newtons, right? So force is a vector, remember, is equal to a mass times acceleration. So mass is not a vector, but acceleration is a vector. And remember, a scalar times a vector is still a vector. So F equals ma. Force is equal to mass times acceleration. Or, really to be more accurate, it's actually the sum of the forces is equal to the mass times acceleration. And this is how we can find the net force and get the net acceleration, right? So if I had 3 or 4 different forces acting on it, I can break it up into its components. I can find I can break it up into its components. I can find the sum, I can find the net force, and then I can get my acceleration. Since we can sum all the force acting on one point by the superposition principle, that's why we can call it this. If I wanted to do it in components, I can also, break the forces into components. So we can write summation of forces in the x direction is equal to the mass times acceleration in the x direction, and summation of forces in the y direction is equal to mass times acceleration in the y direction. And this is what we're going to use the most. You'll be given this on an equation sheet, but you should know that you can break it apart and find your x and y components, because we can do that with everything that we're dealing with pretty much. So this is going to be the easier way to do it. Break everything into its components, find out our summation, find out our accelerations, then we'll put it back. Okay, so talking about a summation of forces in Newton's second law as a sum of forces or sum of components of forces. Let's figure out what exactly we mean by that. So what if, if there's one single force acting on an object, like a hockey stick and a hockey puck, one single force acting on this, it's going to equal some acceleration, right? Force is equal to mass times acceleration. Has some positive force, has some positive acceleration, because mass is also must be some positive quantity, right? We can't have a negative mass. So a puck acting on a frictionless surface accelerates in the same, even if it's frictional, actually, it'll still accelerate in this direction. So a single force acting on an object will accelerate in that direction. But what happens if we have 2 forces that are equal in magnitude but opposite direction acting on a puck, such as we have 2 hockey sticks here, you and your opponent, you're pushing on it in a positive direction, your opponent's pushing on it in a negative direction, you're pushing with the same exact force, so the same magnitude on the same puck here. Well, what's going to be the result? You're just going to sit there and not move at all, right? So the sum of the forces is equal to 0. This I might have, let's say force is equal to 100 newtons. So you have a positive 100 newtons here, but they're pushing back, and because the direction is to the left, this would be a negative 100 newtons. So when I add them up, 100 plus negative 100 would be 100 minus 100, which is 0, right? So we have the sum of the forces would have to be equal to 0. So since we have the summation of forces is mass times acceleration, and the sum of the forces is equal to 0, then we have 0 is equal to mass times acceleration, right? Summation of forces, 100 minus 100 is equal to 0. So 0 is equal to mass times acceleration, but mass is not 0, right? The puck must have some sort of mass to it, right? So mass is not 0, so the acceleration must be equal to 0, because one of those has to be equal to 0, and it has to be the acceleration. So if the forces are equal in magnitude in opposite direction, so there's no force, then there is no acceleration. Or I shouldn't say there's no force, I should say there's no net force acting on an object, then there's no acceleration. So if the sum of the forces, net force, is 0, summation of forces is equal to 0, it means acceleration is equal to 0, and we say the particle is in equilibrium. It is not accelerating. If it's in equilibrium, it is not accelerating. The object can be moving and still be in equilibrium, but it can't be accelerating. If I have something moving along, if this puck, let's say this puck we're already traveling at 5 meters per second, and then I'm behind pushing it, and then my opponent comes up and pushes it, but maybe we're both skating at 5 meters per second, the puck might not be moving relative to us, but it's still moving, but it's in equilibrium because it's not accelerating, it's just sort of moving along at a constant speed. Okay. So, quick little example. Let's find the mass of block 2 right here. If we know that the mass of block 1 and the accelerations A1 and A2. So I know A1, I know A2, and I know the mass of block 1. So I know this one, and this one, and we're going to look for the mass of block 2. So we'll also need to take a note that this is summation of F, this is summation of F, this is summation of F. They're all exactly the same, right? It's not like this is F1, F2, F3 or anything. So all these forces are the same. So the force acting on mass 1 is the same as the force acting on mass 2, which is the same as the force acting on mass 1 plus mass 2. So let's just throw some numbers out there. Let's say that A1 is 2 meters per second squared, A2 is 4 meters per second squared, and mass 1 is 2 kilograms. So we know that F1 equals F2, right? I'm going to call this F1, call this F2, and these are the same. They're both F. Then I know that F is equal to ma. So mass 1 times acceleration 1 is equal to mass 2 times acceleration 2, right? And I'm looking for the mass of block 2. I'm looking for m2. So just doing the algebra here, I say that m2 is going to be m1a1 divided by a2. So we'll have, I didn't write out all the algebra here, so we have m1 times a1, which is 2 times 2, divided by a2, which is 4. So 2 times 2 divided by 4 is 1. So mass 2 is equal to 1 kilogram. So, you know, we have one equation and one unknown, right? And we need to know that we can replace F with ma at any point. And so one of those conceptual things that you have to know for an exam. So let's take it a little bit further and find out what's the acceleration of both the blocks, A3. Now again, I'm going to call this one F3, but it's the same as F1 and F2. So we have F3 is equal to mass times acceleration, so that's mass 1 plus mass 2 times acceleration 3, right? So I don't think I have that written out. F is equal to the sum of these times that acceleration, or this acceleration is just this force divided by these, right? So I have the force was 4. I can find that the force must be mass 1 times A1, which is the same as mass 2 times A2, which is 4 in both cases. 4 times 1 is 4, 2 times 2 is also 4. So the force is 4 newtons, and the mass, m1 plus m2, 2 kilograms plus 1 kilogram is 3 kilograms. So 4 newtons divided by 3 kilograms will leave us with 4/3 meters per second squared. And you can go through and write out a newton as kilogram meter per second squared, and you'll see that the kilograms will cancel out, and we'll just be left with meters per second squared. And we can do some more of these in class, obviously. So kind of what we did here is we found the mass by saying that, okay, I'm going to apply some force to some known mass, and I'll measure its acceleration, right? So I knew all of these. I knew the force, and I knew some m1 and a1. Now, if I didn't know m2, we're going to find the mass of block 2, but I can apply the same force. I can measure its acceleration, and then I was able to find mass 2. And this is kind of a long way to find the mass of something, which we wouldn't want to do if we have scales. So this method may not be very practical if we have some scales around. I can just throw some weight in a scale and let gravity pull it down and measure how much gravity is pulling on it and measure the force due to gravity. But it might be a practical way of finding mass in some instances where we can't use a scale. So where can we not use a scale? Let's get you guys thinking a little bit. What if we were in space where the effect of gravity is minimal? And so we can't use a traditional scale because there's no gravity to pull it down. So we actually might need to use a method more like this to find the mass. Okay, now we're going to get into maybe the most important thing, well, I shouldn't say the most important, but a very critical tool that we'll need in order to solve problems involving Newton's laws and beyond. So we're given this problem. A worker with spikes in his shoes pulls with a constant horizontal force of magnitude 20 newtons on a box with a mass of 40 kilograms resting on the flat, frictionless surface of a frozen lake. What's the acceleration of the box? There's a typical, this is actually a pretty short physics problem. It's only 2 sentences, only 4 lines here. Definitely going to see some that are closer to like 2 paragraphs at some point. In order to get an idea of what's going on here, we need to draw a free body diagram. So what we do, a free body diagram means that the body is this box, right? So this box right here is our body, and we're drawing it free of any other forces. We pretend like it's like the center of the universe. This is the only thing we have here. So we draw every single force acting on this. You only draw forces acting on the body in a free body diagram. So we draw this, helps us draw the box, and then we'll pretend like everything happens at one particular point. So we'll just pick a point right here in the middle because it's most logical to say everything happens at the middle. And then we need to ask ourselves, what sort of forces are acting on this? Well, does the box have a weight? If it has a mass, then it has a weight, and we'll call the weight down here, right? So this is our weight right here. This is equal to mass times gravity. We'll also have a normal force here, right? Is it sitting on a surface? If it's sitting on a surface, it has a normal force. So sitting on this surface here, the normal force is perpendicular to that surface, so it would be directly straight up, right? So that takes care of our 2 of our forces. Our weight is acting down, normal force is acting up. And then we'll just write some other details out here. The mass is 40 kilograms, and I also have this guy pulling on it, which is going to apply some tensional force, right? Because he's pulling with a string. So it's going to be a tension of 20 newtons. So I draw all my forces. I have a weight acting down. You must have a normal force acting up because it's sitting on the surface. And they tell us that a guy is pulling on it. So if he's pulling with a rope, that's a tension. So we'll call it tension is T. You can call it anything you want. You can call it F, you can call it K, whatever, it doesn't matter. We'll call it T for tension, and say it's equal to 20 newtons. So we've drawn that. So now we have everything we need right here. We turned this paragraph into a picture. And now we know that we can use components to solve all these problems. So we're only looking for the acceleration of the box. We actually don't care if it has, we don't care about the vertical components. We draw them anyway because we need the free body diagram to be complete. And if I ask you to draw a free body diagram and you left off the vertical components, it would be wrong. It would be incomplete. So we'll draw these in there, but we're not really worried about the acceleration because these are going to cancel out. I know that it's just sitting here. It says that it is sitting, it's resting on a flat frictionless surface, so it's not moving up or down. So these are equal to each other, so it has no vertical acceleration. Summation of forces in the y direction would be equal to 0. So now I need summation of forces in the x direction is equal to mass times acceleration. So the forces in the x direction is 20. That's the only one here. It's a positive 20 if I call positive to the right. So 20 is equal to 40a. 48x actually. So acceleration in the x direction, 20 equals 48x. So acceleration in the x direction would be 20 divided by 40, or 0.5 meters per second squared. The main thing to take away from this is setting up the free body diagram, drawing all the forces acting on this. You have to ask yourself, you have to know what sort of forces are acting on this, and it takes a lot of practice to know which forces act on it. So practice the free body. So taking free body diagrams to a new level, let's consider something in which we have something moving. We're given information about it at 2 different points. So we have this counter attendant shoving a ketchup bottle, has a certain mass, moves along a level lunch counter. It leaves your hand with an initial velocity. It slides, slows down, and then the bottle slides some distance before coming to a rest. And we want to know the magnitude and direction of the friction. So there's a lot of things going on here. We need a free body diagram to show the forces. So I know, again, this has some weight, it has some normal force, and it has some frictional force going back here. All of these are forces acting on it, so I draw the arrow touching here, and then it moves in some positive x direction. So I'll just kind of denote this off to the side in my free body diagram that positive x is this direction, it travels this direction. Because this is important because friction opposes motion. It's moving this way, so friction must be moving that way. But I don't draw this x attached because it's not a force acting on it. So when I have things I need to show to help clarify the picture, but they're not forces, I draw that arrow off to the side. Another picture that we need is we have a couple different conditions. We have a starting condition of the initial velocity, and we have a finish condition, and we have a distance that it went. So we need to draw another picture to say what's going on here. So it starts off at some starting point 0, and the clerk, the attendant, she pushes it, right? And it starts off an initial velocity of 2.8 meters per second. V naught equals 2.8 meters per second. And we're given a mass is equal to 0.2 kilograms. This is constant throughout, so I'll put that up here. This V naught goes with this arrow. So it moves along, and then it says it moves a distance of 1 meter and ends up at a position 1 meter long here in x. And when it hits there, the velocity becomes 0, right? Because it stops. It moves a distance of 1 meter. It says it moves a distance of 1 meter before coming to rest. So that tells us the final velocity at a distance of 1 meter is equal to 0. So this is where we say v is equal to 0. So with a distance of 1 meter, has a final velocity of 0, has a starting velocity of 2.8 meters per second, and has a mass of 0.2 kilograms. And while it's moving, it had a weight, it had a normal force, and it had a frictional force. So the question is, what's the magnitude and direction of the friction force acting on it? Well, friction force is back this way. Since this is a positive 1 meter, I must have called to the right to be positive x, so friction is negative. So we have the direction is negative already, it's to the left. We need to find the magnitude of it now. So this is example 4.2 from your book. So to save time and size of this video, I'm not going to run through the actual solution, but the idea is that we need to say, well, if we're going to look for the frictional force, I know friction it's a force, so it's still a mass times acceleration, and I have a mass, so all I need is an acceleration. And I can actually go back to what I know from chapter 2 material. I can find the acceleration. I'm given an initial velocity, a final velocity, and a delta x. So I can use v squared is equal to v squared equals v naught squared plus 2a delta x. I can find my acceleration. This acceleration is caused by the frictional force. So once I find that acceleration, I can find, and I have mass, I find my frictional force, and we're there. So run through that in example 4.2. And you should get F is equal to negative 0.78 newtons, negative meaning that it's opposite direction that it was traveling. So I talked about weight a little bit, but I haven't actually given a formal definition of it yet. So let's run through that now. So we know that the mass is a quantitative measure of inertia, right? And inertia is an object's resistance to change. But how is mass related to weight? How are mass and weight related? We can say that weight is a force. Therefore, weight has both a magnitude as well as a force is a vector, right? So it has a magnitude as well as a direction. And what is the direction of weight? If you're standing somewhere or even an object, the direction of its weight is always directed downward, right? So we have the sort of the difference between mass and weight, or the relationship between mass and weight, is that weight is a vector quantity. It's a force, and it's essentially your mass directed downward, right? We also know that from Newton's second law, a force is mass times acceleration, right? In order to get a force, we have to have a mass and we have to have an acceleration. So what accelerates something downward? The only thing that always accelerates something downwards is gravity, right? So you have the relationship between mass and weight is this acceleration, which is gravity. So we have weight, W is equal to weight is equal to mass times gravity. W is equal to mg. This is pretty much the same as F is equal to ma. It's just that we have a very specific case of force. We said weight was a type of force, and we have a specific acceleration. This is acceleration due to gravity. So weight is mass times gravity. Now, so this means that when you say go weigh yourself, you're actually, or go weigh an object, then it's actually a little bit off, because you're not actually looking for the weight of the object. You want to know how much material there is, right? You want to know the mass of the object, right? Weight is how hard do you push on something. It's a force, right? Mass is how much do I have. So not entirely accurate to say what's your weight, but we'll never get away from that anyway, probably. So, but it's important to understand the difference between them. But let's take weight could be how hard do I push on the floor, or it could be how hard do I pull down on a scale. So let's look at a couple different examples. If we're on Earth here, and so we have a mass of 1 kilogram on Earth, and the acceleration due to gravity on Earth is 9.8 meters per second squared. So I know that weight is mass times gravity, so that's 9.8 newtons. But if I were to take this same mass, this same 1 kilogram block, and I were to take it to the moon, and the moon has a smaller g, has a smaller acceleration due to gravity, and this is because the moon has a much smaller mass, but we'll get into that stuff in chapter 6. But the moon has a much smaller acceleration due to gravity, so the mass times the gravity there, the g is 1.62, ends up being a weight of 1.62 newtons. So it weighs much less on the moon, but it actually has the same mass. So this is why astronauts they jump up 20 feet in the air, and they have a long hang time, because there's much less force pulling them back down. So that's the difference between mass and gravity, or mass and weight. You can have different weights, but you have the same mass. Even on Earth, g can vary anywhere from like 9.78 to 9.82 on Earth. So there are some places where g is 9.82, in which you'll have a higher weight. You'll be heavier in those places, but that doesn't mean that your mass is any different. Your mass is exactly the same. It's just that your weight has changed a little bit. So let's run through a quick little example of how we can pull in the relationship between mass and weight in order to solve a problem. So let's say we have this, and we'll practice setting up the free body diagram as well. So we have this luxury car that weighs 1.96 times 10 to the 4th newtons, which is 19,600 newtons, traveling in the positive x direction. So we denote positive x is this way over here, and it makes a fast stop. So it was traveling that way. If it's stopping, it must be going back this way. It must be accelerating back to the left. Force must be the same direction as the acceleration. It makes a fast stop, and the x component of the net force is negative 1.5 times 10 to the 4th newtons, negative 15,000 newtons. So what's the acceleration? So I draw a free body diagram, right? I draw my car here, my positive x, my x direction over here. I know that this isn't a force acting on it, but I know that if it's coming to a stop, it's accelerating to the left. So I'm just going to put this up on the side over here saying my acceleration is to the left. And that helps me actually to determine the direction of my force, right? And the force must be in the same direction as acceleration, so my force must be back to the left as well, or negative. As we call to the right was a positive, to the left must be a negative. And I also have my weight. The weight is given to us. I draw these all the way up to the car, so another force is acting on it. And my normal force is, so that's not accelerating up or down, my normal force must have the same magnitude as my weight, so that my summation of forces in the y direction is equal to 0, because it's not accelerating in the y direction, right? So I have all this, and I want to find what's the acceleration. Well, it's pretty easy, right? Force is equal to mass times acceleration, right? So all I need is mass. I'll take my force divided by my mass and have my acceleration. But what's my mass? I'm given a weight, I'm not given a mass. But I do know that weight is equal to mass times gravity, right? So I can find my mass by taking the weight divided by gravity. I'll get that mass, and then I'll take that mass, I'll take the force divided by my mass, get my acceleration, and we'll have the answer. So acceleration is negative 7.5 meters per second squared. That would be to the left because it's negative. So Newton's third law, one of the kind of a more difficult one, it's conceptual law, kind of. It says that to every action there is always an equal and opposite reaction, which tends to be one that's a little bit more confusing for students. But it's easiest if you think of it in terms of in the equation form. So the force of A on B is equal in magnitude, but opposite direction, so it's negative, of the force of B on A. So force of A on B is equal to negative force of B on A, equal in magnitude, but opposite direction. So from this, let's take this picture right here and let's try to explain this a little bit better. So if A is the force of the rifle and B is the shoulder, so we have A is the rifle, B is the shoulder, then the force of the rifle, there's recoil here, so the rifle is trying to go back this direction, and it applies a force to the left on the shoulder, right? The force of the rifle on the shoulder is to the left, right? Now, if this isn't going to move, if this is going to stay stationary, then I must have another force that keeps the rifle and shoulder from moving backwards, from moving back this direction and to the left. There must be another force going in the other direction, right? Let's say that the force the rifle exerts on the shoulder is 100 newtons to the left. So it's shooting 100 newtons to the left. So by a summation of forces, I'd have to have a force exerted by the shoulder on the rifle of equal magnitude, but this one has to be to the right. So equal magnitude, but opposite direction. So it has to be 100 newtons to the right. So the force of the rifle on the shoulder is opposite, equal in magnitude, but opposite direction to the shoulder, force of the shoulder on the rifle. And next slide will show some more examples of this, but it's important to note that this isn't a cause and effect pair, but it's just an action-reaction pair that exists for any objects that are interacting. So it's not necessarily that the force of the rifle causes the force of the shoulder, or is it the force of the shoulder causes the force of the rifle? It's not cause and effect. It's simply, because they're not moving, there's an action in this direction, then there's an equal and opposite action in this direction, right? So the rifle is 100 newtons backwards to the left, and then the shoulder is pushing 100 newtons forward to the right. So anytime you have two contact forces, or two forces that act in this equal action-reaction pair, and it's really important to know that you only have these two objects, A and B, and they get flipped. So the action-reaction is same object, but they're flipped. So the force of the rifle on the shoulder is equal to the negative of the force of the shoulder on the rifle. Some more of these. So let's determine if these are action-reaction pairs or not. The first one, we have so A, B, C, and D here. So the first one, we're given the force of the earth on the apple. Well, this is the mass of the apple times the gravitation due to the earth. So this is actually the weight of the apple, but we call it the force of the earth on the apple. Now the reaction to this we know should be negative, so opposite direction. Well, that looks good because it's negative. This is down, this is up, so it's opposite direction. The magnitude is the same, it's F, so we're looking good so far, but this is the force of the earth on the apple. So in order for it to be the action-reaction pair, this must be flipped. The reaction must be the force of the apple on the earth. This is not the apple on the earth, this is the table on the apple. So this is A, this is B, this is B, this would be C. There's a third object introduced there, so it's not an action-reaction pair. The action-reaction pair would look like this, but it would have to be the force of the apple on the earth, which is exactly what we have over here in part B. We have the weight of the apple, which is the force of the earth on the apple. The reaction to that must be equal magnitude of F in the upward direction, and it must be the apple on the earth, which is this right here. So this is an action-reaction pair. And by the way, there is a force that the apple exerts on the earth that's equal in magnitude in opposite direction. But we'll cover this in chapter 6. Let's look at letter C here. We have the force of the apple on the table. The apple is pressing down on the table through its weight, right? It's applying some force on the table, and we also have a normal force here of the force of the table on the apple. Now, equal magnitudes of F, opposite directions, apple on table, table on apple. These are switched in these two, so this is also an action-reaction pair. Looking in part D here, we have the same thing we had in part B is this part. So this is an action-reaction pair. Apple on earth is upwards, and then earth on apple is downwards, same magnitude. However, these are not an action-reaction pair up here. We have the force of earth on the apple is down and draws the force of the table on the apple being upwards, but two things wrong with this. First, there is no force that's equal to 0, so it's obviously not the same magnitude. We can draw it to be the opposite direction, but the magnitude is not the same, so we're already not an action-reaction pair. And furthermore, this is earth on the apple, and this is table on the apple. So again, we have three objects, and they're both acting on the apple, so it can't be an action-reaction pair. The two forces in an action-reaction pair never act on the same object. This acts on the apple, this acts on the apple, so they're not an action-reaction pair. Another thing to note is that the two objects change places in the action-reaction pair, and this will always be true. We have earth on apple and apple on earth. Table on apple, apple on table. They're action-reaction pairs.
Okay, now I want to talk about tension a little bit. So an object that has pulling forces applied to its ends is said to be in tension. Like we had the rope back at the beginning of the lecture here. We had a rope where the hand was pulling on it, the block was pulling back, and that gave a tension in the rope. So the tension at any point is the magnitude of the force acting at that point. Okay, so for a weightless rope, chain, or cable, the tension is constant throughout the rope or chain or cable, right? It's if it has mass, then we're increasing the kind of the mass below it, and the tension would vary a little bit. But we're going to talk about massless ropes the majority of the time here. So or weightless ropes, massless as well, then the tension would be constant everywhere. Okay, simplifies the problem quite a bit. So on tension here. So consider a rope attached to a wall here, and I apply 50 newtons of force. What is the tension in this rope? So I apply 50 newtons of force here. It translates to 50 newtons of I apply 50 newtons of force down over here. It translates to 50 newtons of force at the wall here. So what would be the tension in the rope here? Well, the tension is the force it's the magnitude of the force acting at any point in the rope. So the tension here, and this is massless, so we don't need to worry about the weight. The tension would be 50 newtons because we have 50 newtons of force. What about
consider a rope that's being pulled by two people, in which we have a force of 50 newtons down here, and we have a force of 50 newtons down here. What would be the tension in the rope in this case? And you might be inclined to say 100 newtons, but it's not. It's actually only 50 newtons still. So the tensions don't add up. The fact that there are two 50 Newton tensions opposing each other means that the entire rope here is in equilibrium. Okay, it doesn't mean that the tension is 100 newtons. It just means that, there's no, if I were to free body diagram this whole thing here, I would have my summation of forces would be a negative 50 and a positive 50 that add up to 0. So the entire thing is not accelerating. So the fact that we have these two opposing forces of 50 newtons means the tension is still 50 newtons, but the rope is not moving. There was actually, in the previous slide, the wall was actually pulling back on the rope at 50 newtons as well, but hopefully we didn't say 50 newtons there was the tension, or hopefully we didn't say 100 newtons there, it was just 50 on the wall. What about if we have a rope being pulled by two people, and there are different forces? One is 50 newtons to the left, and one's 40 newtons to the right. Well, the tension in this rope would be 40 newtons, right? So now the difference in the forces causes a net force to the left and an acceleration to the left, right? So there's going to be 50 newtons over here to the left, 40 newtons to the right. We're going to have a net force of 10 newtons to the left. So it's going to cause an acceleration to the left. But the tension and the force, the tension in the rope is the force that acts throughout the entire thing. There's actually only 40 newtons of this acts as a tension, and the other, so 40 newtons in this rope acts as a tension, but the other 10 newtons causes an acceleration. There's only 40 newtons of tension in this rope in this case. So essentially it's going to be your lower one. If you have a net acceleration, then your tension is going to be whichever the lower force is. Okay, just a little touch up now on free body diagrams. We've talked about them a little bit already. But if we're interested in why an object moves, we need to know exactly what forces are acting on it. And there's pretty much always going to be more than one force acting on the object. So we need to use a summation of forces. Okay, so we have essentially two different cases here when we're evaluating the free body diagrams. We either have, if the object is in equilibrium, which a lot of times we're going to have to tell from the given information if it's in equilibrium. So if the object is in equilibrium, then we're going to have a summation of forces is equal to 0. If an object is not in equilibrium, then if it's not in equilibrium, it's accelerating, right? So the summation of forces is equal to mass times, however fast it's accelerating. So these are basically the two equations we're going to use for our summation of forces. Right now, we'll add some more in later. But these are our two kind of starting ones. Either it's in equilibrium or it's not. But the trick to solving these free body diagrams is finding out what object we need to apply these summations to. We have to kind of practice getting that out of the information given to us in the paragraph. So, and we also need to be very careful that the forces we include in the summation are only forces that act on the object. They can't be forces the object is applying to something else. It has to be forces acting on the object. Okay, so we're not going to include the entire action-reaction pair. We only include half of that action-reaction pair because we're trying to figure out what object is accelerating, right? I need to know what forces are acting on one object to find out how it's accelerating, or what object is in equilibrium. Well, what forces are on that object to make it in equilibrium? So once we choose the object or the body, we must find all of the forces that act on it. So one of the most powerful tools we have is the free body diagram, which we've seen a couple of them already. And to draw a free body diagram, we draw the object, don't make a very detailed sketch of it, just like a box or something works
just as good. So we draw the object, and then we draw and label all the force vectors that act on the object, everything that acts. So let's think about the apple that we had earlier that was sitting on the table. We want to draw a free body diagram for this. So a couple of things, ways we have to think differently in physics. So we need to sit down and think, what sort of forces act on this apple? Well, this apple obviously has a weight, right? So it must have some mg, some mass times gravity pulling down on it. But we also need to say, well, is this apple, if it has a force acting downward, does it have a force acting upward? If it's not moving, then it must have a force acting upward as well. So our free body diagram, and we say there's no forces acting to the side. We didn't have any drawn, we didn't have any given to us. So there's no forces acting to the sides. So the free body diagram here, we would draw the weight acting down and then a normal force acting up. Okay? Now, this is physics. It's not a math class, it's a physics class. So we have to think about the physical situation in order to apply the correct mathematical formulation. This is where it gets completely different. We have to take some of the concepts and the concepts from the physics, and we have to figure out the right math equation, mathematical formulation to figure it out. So what's going on physically? What is happening to this apple? The apple's just sitting there, right? So there's nothing going on other than it just sitting there. Well, to say there's nothing going on is completely wrong. So it's sitting there, it's not moving, it's not accelerating. So it means that this weight right here must equal this normal force right here. There must be no net force to cause a net acceleration. So it's equilibrium conditions that are going on here. It's not moving, it's not accelerating. So it's in equilibrium conditions. So summation of forces is equal to 0. So I add these up. I could say summation of forces in the y direction, put a little y here, say they're equal to 0. So normal force has to equal the weight. And we can find the normal force. Let's do another free body diagram here. So let's say we have, this was part D before, we remove the table. We have the force of the apple on the earth, the force of the earth on the apple, and there is no more force of the table on the apple. It's equal to 0 now, right? So the free body diagram, what are the forces acting on this thing? What are the forces acting on the apple? We're going to free body diagram the apple. So the forces acting on it, well, the force of the table acting on the apple is irrelevant to draw because it's equal to 0. Draw the force of the earth on the apple, well, that's something on the apple, so let's draw that one. Force of the apple on the earth, not acting on the apple, so don't draw it. So the only force we have is the weight, right? The force of the earth on the apple. But something is happening here. It's moving, right? It's accelerating downward. This is obviously falling and it's accelerating downward, so I need to put my acceleration off on the side. That helps to indicate what's going on physically. So this is my force, it acts on the body, so I draw a force touching it, right? And then I have an acceleration. I know it's accelerating downwards because that's my intuition, the physics, and so I draw an acceleration vector downwards. So what's going on physically? It is accelerating. So which equation do we use? We have to use summation of forces is equal to mass times acceleration. Right? So we have to think about, we use a figure to help put everything together, right? But with this figure, we put a lot of thinking into it. What's going on physically? Draw that picture. And then by knowing physically what's going on, we can use the correct equation. And then I simply say, so weight is mg. mg equals ma, because that's mass times acceleration. So if mg equals ma, then it's accelerating at a rate of g, right? So we can say it's accelerating downwards, which makes sense, right? As long as we don't have. So we can apply free body diagrams to any sort of situation or any sort of scenario here. Let's say we have a runner pushing off on a block to get going. We know, in the equilibrium conditions or the acceleration conditions, we can find a lot out with just a little bit of information here in a free body diagram. let's say we're given the mass of the runner and the force that she exerts on the block. From that, we can find the angle here, we can find her weight, obviously, and we can find the acceleration at which she pushes just by giving the mass and the magnitude of the force. So we can do this because we know that she's not accelerating vertically, right? She's not trying to jump here, she's trying to push off in the x direction. So this magnitude times the sine of this angle, sine of theta, must be equal to Fy, right? But Fy, if she's not accelerating, must be equal to the weight. So I can say that the y component of force is equal to this force times the sine of theta, so we can find theta. We can find this angle right away, because this times the sine of theta is equal to the y component. So find theta, and then we can go back and then the x component of the force is just this times the cosine of theta. So now we can find the x component of her force, right? So we found the x component of her force. We were given a mass, then force is mass times acceleration, or acceleration is force over mass. We can very easily find her acceleration. So just by knowing the magnitude of the force and her weight, we can find her acceleration forward. So there's a lot of things we can find by putting a free body diagram together, and knowing, breaking it into x and y components, and knowing equilibrium versus dynamic conditions. We'll do many of these in class. Chapter 5 is nothing but solving problems like this, so we'll do a lot of these in class. Please come prepared with questions. And that's it.